Alrighty, good morning, lads and ladies. Welcome back to Calc 1. Today is your day. Today is our review for the third exam. So whatever it is you guys wanted to talk about, we are going to talk about today. So I will flip on the document camera here in just a second, and we can start taking questions from homework. If you want to ask a question from the study guide, you can, but as always, I'm not going to solve the study guide problems entirely. I can either solve a similar one or give a little hint or a little discussion on the concept. But yeah, that's it. Oh, that's sweet of you, Mackenzie. I've been having technical problems with this survey the whole time it's been here. It originally didn't even show up in my AQ Canvas course, so I'm not too sure what's going on. I definitely appreciate you clicking the link. If it's not working for you, then it's not working, and there's really not much we can do. I emailed their people a couple times over the week, and they were like, no, your stuff is working fine. I sent them a screenshot. I was like, no, it's not. So I think some of these folks are a little bit technologically challenged, and it is what it is. Well, I definitely appreciate you guys trying. Maybe I will let me hit them with an email really quick and see if they can. Okie dokie, yeah, so I just hit them with one more email. We'll try it. And if you do have time to take one more stab at that later in the day, that would be great. But if you don't, again, I totally understand. I am short on patience for their bullshit at this point. It's been a very tedious class, but it has been neat. Don't let my negativity about the survey reflect poorly on AQ. If you do ever end up teaching, you do ever get an opportunity to take a course like AQ, it's a nifty thing, and a lot of people do put a lot of love into it. But some of them are not the most tech savvy folks in the world. So on to our business for today, the review, right? So whatever you guys would like to see, we can work on. This is MAC2311.002. Today is the exam 3 review. The date is the 16th of April, 2021. So, okay, we can start with homework 13, number 1. As always, feel free to just hit the chat, with homework blank, question blank, whatever you want to see. So here's our homework sets. Homework 13, number 1 was the first one we asked for here. So I want to find the area of this shaded region. Okay, sure. So this is sort of the nicest of all possible cases where we're looking at an area between curves problem. Homework 13, problem 1. They sketch it for us, which is kind of them, because normally the first step here is going to be for us to draw the picture. And the two curves are 1 over x, which has this familiar shape that we've been seeing a lot in these problems. That's quadrant 1's bit of 1 over x, and the other guy is the cube root. Who has this sort of look to him. y equals 1 over x. This is y equals the cube root of x. They tell us that the point right here is 1, 1. And they also drawn in a vertical line over here and marked that as x equals 27. So the enclosed region here, pencil disappeared. I like shading these on pencil. Oh, there's not one. So the enclosed region we have is this stuff. I say no, find the area of this shaded region. So remember the game, when trying to find areas between two curves, if they are both given with y as a function of x, as is the case here, we need to integrate from a to b, the upper function minus the lower function dx. Where x equals a, this is the leftmost x value in that region, or the smallest x value in that region, and b is the largest x value in that region. This is sort of the mnemonic. So for this particular guy, the smallest x value anywhere in this region, right, you think about this whole shaded region here, the smallest x value anywhere in here is 1. And since this line is x equals 27, we know that the largest x value in this region, or the upper bound there, is 27. Sometimes it's helpful to draw those like a single approximating rectangle in here to kind of help you get a feel for what it is that you're doing. So in this case, that would look like that. The width of this rectangle is thought of as dx, and then the height of this rectangle would be whatever the y value is up here minus whatever the y value is down here. So the y value up here is the cube root of x, and the y value down here is 1 over x. So this would be the cube root of x minus 1 over x dx. And that's the setup. And the majority of these problems, once you have the integral set up, you're in fairly good shape. Usually the integrals themselves here are not really the challenge, although they certainly could be. Integrals can be hard as balls, but most of these problems, the integrals are pretty straightforward. It's just about getting the integrals set up correctly. So are there any questions up to this point? Okay, then the only thing I would do before crunching out my antiderivative, I would rewrite the cube root of x as a power to help me see what that antiderivative is going to be. So remember, the cube root of x is the same as x to the 1/3. So we have x to the 1/3 minus 1 over x dx. And sort of the rule there is that the nth root of x is the same as x to the 1 over n. So now we have this in a form where I can pretty much just read off an antiderivative. We can use the power rule on the first piece. And an antiderivative for 1 over x is the natural log of the absolute value of x. So I am ready to take my antiderivative at this stage. I'm going to bring it back over to the left. When I add 1 to this power, so this piece is the piece I use the power rule on. When I add 1 to 1/3, I get 4/3. So this would be x to the 4/3 divided by 4/3. And then that minus is this minus. And then an antiderivative for 1 over x would be the natural log of the absolute value of x. And this is a definite integral. I don't need any plus c. I just evaluate this between the bounds. I think it's wise to simplify this piece before plugging in any balance. It's a fair question. So should we write 1 over x as x to the -1? You can if you want to. It's not going to hurt anything, and it's not incorrect. But it's not really helpful for the antiderivative there. See, for every other power function, kind of remember those antiderivative rules. Squeeze them in down here. Antiderivative for x to the p dx is x to the p plus 1 over p plus 1, plus c if I'm writing it like this. But this is only valid for p different from -1. And then if you're integrating x to the -1 dx, I always remember this as that's the same as 1 over x dx, because that's usually how we write the derivative of the natural log. So the antiderivative of 1 over x would be the natural log. So these are sort of the antiderivative rules in play here. Oh, sorry, switched back to black. These are the antiderivative rules in play here. So I rewrite power functions as power functions unless that power is -1. Right, so if I have like a cube root or 1 over some power of x, I will always rewrite those as a power, like you're saying, Fabrice, except for 1 over x. This is the only one I don't do that for, and that helps me remember that he's the one that gives me the natural log, and that everything else follows the power rule. So while you could do it, I'd argue that it's not necessarily helpful, but it's up to you. It's your choice. From here, like I said, I would simplify the first piece. So this is 3/4 times x to the 4/3 minus the natural log of absolute value x. And that's evaluated still from 1 to 27. And now we will actually plug those things in. So this is, I like to put these in parentheses, 3/4 times 27 to the 4/3 minus the natural log of 27. The absolute value of 27 is 27. And then from that, we subtract 3/4 times 1 to the 4/3 minus the natural log of 1. Again, the absolute value of 1 is just 1. And hopefully we're all remembering that the natural log of 1 is 0. 1 to any power is just 1. 27 to the 4/3 is a little bit more interesting. Well, so here I'll have 3/4 times. Remember how these powers work. Raising something to the 4/3 is the same as taking the cube root and then raising that to the 4th power. So what's the cube root of 27?
3. Is it 9? I mean 3?
It is 3, yeah. 27 is 3 times 9, which is 3 times 3 times 3. So 27 is 3 cubed. So the cube root of 27 is 3. So this is the same as 3 to the 4. And 3 to the 4 is 9 times 9 is 81. So 27 to the 4/3 power is 81. So you have 3/4 times 81 minus the natural log of 27. And then over here we have minus 3/4. Because again, the natural log of 1 is 0. So this is where we end up. You could leave it like this, or you could combine the two rational expressions. This and this could be combined. They do have the same denominator. 3 times 81, I don't remember off the top of my head, but it would be 3 to the 5. But this would be fine. You could leave it like this. Okay. Any questions on this fellow before I move away from him? We got drama with the kitties again this morning. Sorry if you're hearing that. All right. So the next question that was requested is something similar to study guide 3, number 20. So let me pop the study guide here. If there's some RNG in that, we can make use of it. A little bit. So we could do x to the 4 over 1 plus x to the 10. That would work. I think we've talked a little bit about integrals of this form. We've seen certainly a few of them. I'm curious what comes to your minds when you see this. So does anybody have a thought immediately when they look at this thing?
U equals x to the 5th.
Very good. Yeah, Mackenzie's nailing it. So the x to the 10 downstairs, remember that's the same as x to the 5 all squared. And the x to the 4 upstairs is very similar to the derivative of x to the 5. So this is kind of looking like it's going to be a u sub thing, where u would be x to the 5. And to help us see that, it's that algebra trick again. Where, you know, x to the 10 is the same as x to the 5 all squared. So if we gave the problem like this, I think most people would recognize that the game is to substitute for x to the 5. Because then du is going to be 5x to the 4 dx. And I have an x to the 4 upstairs here, which will cancel nicely with this. It's kind of like chess, you got to look one step ahead. I'll plug in just the obvious piece for now. Or just the piece that we substituted for, the thing that invited us to make that substitution in the first place. And then our next step is to solve this expression for dx. This is the same as saying 1 over 5x to the 4 du is equal to dx. So in place of this dx, I can plug in this whole expression. So I've got still up here my x to the 4, down here my 1 plus u squared. But then this dx is the same as 1 over 5x to the 4 du. And lucky us, the x to the 4's go. There's a factor of 1/5 that can come out. And then I'm just looking at the integral of 1 over 1 plus u squared du. Are we comfy up to here? Are there any questions about how we got to this point?
How did you get the 1 over 5x to the 4th du equals dx?
So I'm taking this guy right here and I'm solving it for dx. So I want to get this piece alone so I can plug in for the dx. So when I solve this for dx, I have to divide both sides by 5x to the 4. So you could write it as du over 5x to the 4 if you wanted. That would also be fine. But I'm just taking this expression here and I solve it for dx. To do that, I have to divide both sides by this piece. And that gives me.
That makes sense. Thank you.
Yeah, no problem. Any other questions about how we got to this step? A little word of warning, something I've seen a lot is this 5 showing up outside, but upstairs. So you got to remember, this is a 1/5. He's downstairs. He comes out as a 1/5, not as a 5. Any other questions about the steps here? Okay, cool. Yeah, this algebra trick, this is really the game, right? Is like rewriting x to the 10 as x to the 5 squared. That's kind of the thing that helps me see this, because once I see that, I realize, oh shit, this is like very close to the derivative of x to the 5. So that algebra rule is very useful. But x to the a times b is the same as x to the a all to the b. Sneaky algebra rule, but useful surprisingly often. All right, so from here, what do? If we're happy here, what is the indefinite integral of 1 over 1 plus u squared du?
Arctan.
Very good. This is the inverse tangent of u. Because the derivative of arctan u is 1 over 1 plus u squared. And then because it's an indefinite integral, we do have to go back and plug in for u. So this would be 1/5 times the inverse tangent of x to the 5th plus c. This one's story time. We brought that, so that stray cat that's kind of been coming in and out of the house and being very sweet, we're trying to find a home for. We brought him inside last night, and he's adorable and lovely and snuggly. But this morning it seems like our two cats have noticed his smell, and so they are losing their fucking shit. Basically, it's pretty funny. Anyway, remember, if anybody wants a cat, this one is a very sweet cat. So that was study guide 3, problem 20. So our next requested problem was 13.5. So this one was the study. I'll leave this open. 13 number 5. All right, so here we have y equals e to the x, y equals x squared minus 1. And our other boundary curves are the vertical lines, x equals -1 and x equals +1. So I think this one comes down to graphing. These are definitely curves that I would expect you to know how to graph, and this could easily show up on a test. This is very much a test caliber problem. So we want to find the area of the region bounded by y equals e to the x. Was it 1 minus x squared or x squared minus 1? X squared minus 1. Y equals x squared minus 1. X equals -1 and x equals +1. I remember that equations like x equals a constant, these are always vertical lines. Y equals a constant is a horizontal line, x equals a constant is a vertical line. Because you're saying, like, no matter what y is, no matter what you choose for the other variable, x is always -1. So like -1, 0, -1, 1, -1, 2, -1, 3. Those all live along this vertical line. The other two here are kind of standard graphs. E to the x, this is a growing exponential. Definitely a graph we should know. And this fellow is a parabola, the standard y equals x squared parabola, just shifted down 1 unit. So I'll do my best to give us a nice little drawing here. E to the x looks something like this. And if I mark this as -1, then x squared minus 1 looks something like this. X squared minus 1, remember, has the two x-intercepts at 1, 0, and over here at -1, 0. And normally I don't really care about intercepts for the purposes of these area problems, but I plot those to kind of help us see where these lines are going to come into this picture. So the last two things here I'll draw in purple. Vertical lines, because this whole region here is not the same as the region whose area we're asked to find. There's x equals -1. Here's x equals +1. So the kind of little tiny piece over here, not interested in him. The little tiny sliver over here, not interested in him either. I just want the stuff that's between the black curves and between the purple lines. So just this stuff. And without those purple lines kind of making the boundaries there, this would be considerably harder. I'd like you to think about why that is. The intersection points of the parabola and the exponential there are quite hard to find. So think about that a little bit. Okay, this is my x-axis, this is my y-axis. We've got everything drawn and labeled. I hope you guys can see what I'm talking about here. This tiny little piece here is a piece I'm not interested in, as is this over here. So I'm just looking for the stuff that's between -1 and 1, bounded above by e to the x and below by x² - 1. From here, it's fairly straightforward, right? We integrate the upper minus the lower from the left boundary to the right boundary. So the leftmost or smallest x value in this region is -1. And the rightmost or largest x value in this region is +1. So I'll have integral -1 to +1 of the upper function, which is e to the x, minus the lower function. Remember, if it's got more than one piece, you need to put it in parentheses, x² - 1. And the integral is done dx. So that's going to be my area. And from here, not too bad, right? You can distribute that negative. 1 e to the x minus x² + 1. We can find our antiderivative. E to the x stays e to the x. And we have minus x³ over 3, or 1/3 x³, plus x. The last two following from that power rule again. The integral was -1 to 1. So to finish things up, we have to evaluate between those endpoints. When x is equal to +1, we have e to the 1 minus 1³ over 3 plus 1. And from that, we subtract what we get when we plug in our lower bound, which is e to the -1 minus -1³ over 3 plus -1. And there's some simplification that can be done here. I'll try to do this cleanly. So this is e minus e to the -1. That's e minus 1 over e. Here I have a -1/3. Right, 1³ is 1, so 1³ over 3 is 1/3. -1³ over 3 is -1/3. And then here I have a minus. And then what is this piece? So this is -1³, which is -1. So this piece here is -1/3. But it's being subtracted here. So that makes this a +1/3. But then we also have this negative to distribute. So the net contribution from this term is a -1/3, and it goes negative, positive, negative. So I have a -1/3 here and another -1/3 from this. That's -2/3. And then the net contribution from the ones, I've got a +1 here and then a -1 here. So that's going to be +2. And again, you could combine the rational terms, the 2/3 and the 2, but I say leave it, it's fine. Questions on this, Phil? Yeah, so the x cubed over 3 is an antiderivative, right? When I want to antiderive x squared, we get x cubed over 3, and then the x comes from the 1. Looking up there, the reason on the previous problem to change x to the 10 to x to the 5 squared is to help us see the substitution. So say anytime I see an integrand that kind of looks like this, specifically a factor downstairs that's like 1 plus an even power of x, or 1 plus an even power of something else. It doesn't have to be an x, could be like 1 plus e to the x squared. Anytime I see a factor of the denominator that kind of has that shape, 1 plus a constant, or 1 plus an object to an even power, my brain immediately goes arctan. Right away, it makes me think of the inverse tangent function, because I know that the derivative of the inverse tangent function is 1 over 1 plus x squared. So when I see the 1 plus x to the 10, I start thinking arctan, which tells me I want to write this as something squared. And that's what motivates this being rewritten as x to the 5 squared. And once we do that, then we can see that the top is a constant multiple of the derivative of the inside, because the derivative of x to the 5 is 5x to the 4. So that's what kind of motivates, is that as soon as I see something downstairs that looks like this, my brain thinks arctan, okay, let's rewrite this as the square of something else. And it even works when the powers aren't even, like you can force it using fractions, and there are problems like that that still work out. All right. Any other questions or comments on this fella? The minus 1 over e is coming from this minus e to the negative 1 term. E to the negative 1 is 1 over e. It's like anything to the negative 1 is 1 over that thing. So I have a negative here that needs to be distributed. That's going to flip the sign of all 3 of these terms. And the e to the negative 1 is 1 over e. Other questions on this one? Okay. I think the next few problems that were asked for, that was homework 13 number 5, right? Study guide 19. Okay, and then I think study guide 19 is the last one that anybody's asked. So while I'm setting this up, feel free to look through and find something else if there's anything else you want to look at. Oh, yes. I saw that earlier. Some Riemann sum problems. Sure. This is a great problem. So we've got e to the cosine of 39t times the sine of 39t. All right. Flip around the sines and cosines. This is study guide 3, number 19. Let's say this is e to the sine of 42t times just cos. Yeah. So I'll just write cos of 42t. Any Douglas Adams fans? Anybody know the significance of the number 42? It might be something that is of a slightly older generation. It was even slightly before my time. But if you haven't read Hitchhiker's Guide to the Galaxy, I recommend it. It's a great book. Who can help me out here? Does anybody see a substitution or even a pair of substitutions that could help simplify this integrand a little bit?
Sine 42t.
Yeah, and it would be understandable if you wanted to do it in multiple steps also. I think the most obvious inner function here is the 42t. So you could just start by subbing for 42t if you wanted. Or looking a little bit further down the road, realizing that this is e to something and something very close to the derivative of that something, you could try to sub straight away for the sine of 42t. And I think that's understandable. So let's try that. Let's make u the sine of 42t. What is du?
Negative cosine or 42, negative 42 cosine t dt.
We're close there. So it's easy to get derivatives and antiderivatives kind of confused with sine and cosine. The derivative of sine is cosine. The antiderivative of sine is negative cos. So you're correct, modulo that negative. So if I differentiate sine of 42t, I'll get cos of 42t. And then by the chain rule, I have to multiply by the derivative of the inside. The derivative of 42t is just 42. And then we have our dt here. So this would be my differential. Now the actual problem from the study guide has the sines and cosines flipped around. So if you are subbing for cos 42t, as you will in the problem, you wouldn't get a negative here because the derivative of cos is negative sine. All right. I notice that I've got a cos of 42t here, and I've got a cos of 42t here. So I'm expecting some nice cancellation. But if we kind of just follow the pattern we've been following, e to the sine of 42t is going to be e to the u. And I'll leave everything else in this step. Remember, there are other ways to think about this that are slightly faster, perhaps more sophisticated. But if you're wanting to be very careful, you can take it in these steps that I'm showing you. You plug in the thing you chose to substitute for. Then you can come over here and solve for dt. And there I would see that 1 over the cos of 42t times 42 times du is equal to dt. So then this integral will become e to the u cos of 42t times 1 over cos of 42t times 42 times du. Mackenzie asked a question in chat. When we're making a substitution in a definite integral, into what must we plug the old bounds to get the new bounds? Into the substitution. So like if this original guy was an integral from 0 to pi, if it was a definite integral from 0 to pi, to get my new bounds, I would plug in t equals 0 here, and that would give me the sine of 0 to 0. And I would also plug in t equals pi, which would give me the sine of 42 pi, which is also 0. So I guess bad example. But yeah, you plug into the substitution. We can look at an example if you want. The nice thing here is that the cos of 42t's cancel. And we're left with just the constant factor 1 over 42, which can be popped out. So I have 1 over 42 e to the u du. An antiderivative for e to the u is e to the u. So this is 1 over 42 times e to the u plus c. And then because it is an indefinite integral, we do go back to the bound, the original variable here. So this is 1 over 42 times e to the sine of 42t plus a constant. So Trent wanted to look at a problem like number 4 on the study guide. Before we move to that, any questions here? Okay, and after we look at Trent's problem, Mackenzie, we can look at a definite integral via u sub to rehash those. But first, let's go back to the study guide and scroll up to number 4. We can try to find something similar. This isn't the study guide, is it? This is, oh, it is, yeah, okay. Oh, yeah, okay. And we also wanted to look at Riemann sum stuff. So we'll look at a separate Rn problem right after this. Express the integral as a limit of Riemann sums. So this is like the thing we were talking about on Wednesday, when it's like, you know, what sort of Riemann sum E questions could I force you to do on a test? This would be a good example of something I could ask you to do on a test, right? Give you an integral and say, you know, write this using the definition as a limit of Riemann sums. That would be kosher. So here the integral is from 2 to 4, and the integrand is root 5 plus x squared. So let's look at that. It was asked the other day in class, you know, if you're given a problem like this, must you kind of follow the instructions, or can you solve the integral using the fundamental theorem? A well-designed test question would be one where you don't know how to resolve the integral using FTC. And this is an example of that sort of thing. The tools that are needed to find an antiderivative for this are beyond us. We don't have the tools. If there was an x out front here, then I could do it with u sub, but there isn't. So this would be a good example of a challenging problem like that. Now, the limit of the Riemann sum at the end here is also going to be quite hard. That's why they're not asking you to evaluate it all the way. They just want you to say, what will this turn into as a limit? So before I jump in, I just want to remind you that the integral, if f is integrable, the integral from a to b of f of x dx is defined to be the limit as n goes to infinity of the sum sigma I from 1 to n of f of xi times delta x, where delta x is b minus a over n, and xi is a, your lower limit, plus I times delta x. So this is what we need to get this down. And you notice how quickly that rolls off the tongue, right? I mean, I know it's not like a nursery rhyme, but this is something we just need to remember. It's something you must commit to memory. And it's not that bad, especially if you think about all the pieces. Kind of the integral is like the sum, the f of x is like the f of xi, the delta x is like the dx. So delta x should be the width of each rectangle, which is the total length of the interval divided by the number of rectangles. And xi is the right endpoint of each subinterval. So you start at the leftmost point in your interval and add I copies of the width to get to the ith subinterval. So to get started on something like this, you need to first write this down, or at least remember this, and then first step, calculate delta x. Delta x here is b minus a over n. That's 4 minus 2 over n. 4 minus 2 is 2, so that's 2 over n. We need delta x in order to write down xi. Xi is a plus I delta x. A is 2, so that's 2 plus I times delta x is 2 over n. F of x here, of course, is the square root of 5 plus x squared. So f of xi is the square root of 5 plus xi squared. And the xi's are the things we just wrote down. So this is 5 plus 2 plus 2i over n. Squared. This is our f of xi. So now we just plug this stuff into the definition above. So the integral from 2 to 4 of the square root of 5 plus x squared dx. The limit, that's n, goes to infinity of the sum from I equals 1 to n of f of xi, which is the square root of 5 plus 2 plus 2i over n squared times delta x, which is 2 over n. That's it. That's it. So they asked you just for this piece. Of course. All right. What other stuff did we want to see? So I'm going to talk a little bit about left and right Riemann sum, something kind of explicit. Let me just invent a little problem here. I can ask you to approximate the integral from 1 to 3 of something we don't know how to do. Natural log of x dx using R6. So remember, Rn is the sum I equals 1 to n f of x I times delta x. It's the thing that we're playing with in the previous problem is Rn. So and this is the shorthand for f of x1 plus f of x2 out to f of xn times delta x. Now, maybe let me just for brevity's sake, let me change this R6 to R4. We're going to be here all day. So R4 would be f of x1 plus f of x2 plus f of x3 plus f of x4 times delta x. So as with all these problems, you need delta x and you need xi. So here, delta x is b minus a over n. That's 3 minus 1. And in this case, I'm using R4, so n is 4. 3 minus 1 over 4. That's 2 over 4, or 1/2. And that means xi is always a plus I delta x. It's going to be a is 1 here, so this is 1 plus I times 1/2, or 1 plus I over 2. And I think it can be helpful to just list the xi's. So x1 here would be 1 plus 1/2 is 3/2. I'm just plugging in for i's. X2 would be 1 plus 2/2, which is 1 plus 1 is 2. X3 would be 1 plus 3/2. And what is 1? I'm sorry, 1 plus 3/2. 1 is 2 over 2, so 3/2 plus 2/2 is 5/2. And x4 would be 1 plus 4/2, which is 3. So R4 here is f of x1. Well, what is f of x here?
Three over 2.
x1 is 3 over 2, but I need f of x1. Let me write it like this. This is f of 3/2 plus f of 2 plus f of 5/2 plus f of 3 all times delta x, which is 1/2. But what is f? What's the function f?
ln.
Very good. F of x is the natural log of x. So this would be the natural log of 3/2 plus the natural log of 2 plus the natural log of 5/2 plus the natural log of 3 all times 1/2. And this would be your final answer. All right, I could ask you for a decimal. You could plug this stuff into your calculator, but on the tests, remember, calculators are not necessary for this class. And it's not something that I would ask for. So this would be the answer. This is R4. There's plenty of stuff we could do to try and simplify this if we wanted to using natural log rules, but it's not really not worth doing. The point is showing me that you are familiar with Rn and you know how to utilize it. That's what these problems would be about. All right. I think the other thing that was asked that we haven't gotten to yet is just a little bit of definite integral work using U sub, specifically like bound changing stuff. So first, are there questions on what we've done here? All right, then let me swoop into our book, find some U sub stuff. We spent enough time on this that I'm starting to run out of examples to grab that I haven't done in class. I've given you as homework at some point. But that reminds me, that would be good.
If you can't find one, I don't specifically need one. I just forgot the specific like interchanging U's and X's. But I understand it now.
I think I got something good for you here.
Okay.
How about the integral from 0 to pi over 6 of sine t over cos squared t? I like that.
Okay.
Believe it or not, this can be done without U sub, but I do think that U sub, especially when it's written in this form, is the most natural way to do this. You can write this as secant t times tangent t, and then we could spot an antiderivative right away. So maybe we don't need U sub here, but we could attack it as a U sub problem. Does anybody see a way to attack this as a U sub problem?
U equals cosine t.
Very good. So if I make the substitution, U equals cos t, then du would be the negative sine of t dt, because the derivative of cosine is negative sine. And because this is a definite integral, we also need to work with the bounds. So when t is equal to 0, that's my old lower bound, u would be equal to the cosine of 0. I have to plug in to this relationship here, the old lower bound, which is a t value, because the old integral was a dt integral. So u would be the cosine of 0, which is 1. I'll write it out like this. And then when t is equal to pi over 6, u would be the cos of pi over 6. Now, who remembers the cosine of pi over 6 from the unit circle?
Is it square root 3/2?
It is. Yeah, remember pi over 6 is less than halfway up. It's less than half of a rotation. It's before pi over 4, which means that we've not gone up as far as we've gone out, right? If I rotate halfway, that means I'm exactly halfway up and halfway out. That's the root 2/2. So before that, my x value cosine will be larger than my y value. So rather than being the 1/2, it needs to be the root 3/2. Good question, Holly. If I rewrite the integral as integral 0 to pi over 6 sine of t over parentheses cos t all squared dt, then the only part of this that has like an inner and an outer is the bottom. Downstairs here, I have the squaring function as an outer and the cosine function as an inner. So subbing for the inner function in the chain rule looking thing is usually how we choose our u's. And then the other kind of hint is, once you see this, once you think, oh, maybe I should sub for cosine, we realize that the derivative of cosine or something very close to it is floating around to be canceled later by our differential. But the main hint is that the bottom is cos t all squared. So that is an inner and an outer, and the inner is cosine t. So that's what will make you, I think chain rule, whatever is your inner chain rule wise would be your u. So under that substitution, this integral is going to become integral when t is 0, u is 1. So integral from 1 to when t is pi over 6, u is root 3/2, integral 1 to root 3/2. And then I'll leave the sine t alone. I'm just going to plug in the obvious thing here. The thing I chose to substitute for was cos t. So this is going to be u squared downstairs, and I'll leave the dt for now. And then in my next line, I will plug in for dt. These in-between steps are technically not kosher, but they're very useful to kind of guide you to the result. So remember, the goal, again, long-term, is to get you to a place where you don't need to write these in-between steps. You can just kind of see where everything's going to go. But you guys are still learning, so it's okay. We solve this for dt. Since du is negative sine of t dt, we learn that 1 over negative sine of t du is equal to dt. So in place of the dt, I will write negative 1 over sine t du, or 1 over negative sine of t du. And these are multiplied, right? So there's a factor of -1 that will remain, but there's a factor of sine t upstairs and a factor of sine t downstairs, which can cancel. The -1 from this guy can pop out. And I have negative integral 1 to root 3/2, 1 over u squared du. And again, the goal is eventually to be able to arrive here immediately without writing these in-between steps. But don't hesitate to write them if they help you.
This is a weird algebra question, but why can the sine t and the negative sine t cancel? Isn't there still a negative
Yeah.
on the bottom?
So that negative is right here. It's a good question.
Sorry.
No, don't feel bad. If these were being subtracted, if this was this thing minus this thing instead of this thing times the negative of this thing, then they could not cancel. So I'm actually really glad you asked that. It's an algebra thing that I see all the time. The rule here is we can only cancel common factors. And if I wanted to, I could rewrite this as the sine of t over u squared times sine t with a negative out front, right? So kind of the algebra step that's going on in between there is multiplying these fractions together. If I multiplied those fractions together, this is what I would get. And so we see that there is a common factor of sine t. The top is sine t times 1. The bottom is u squared times sine t, so they can cancel. But if these were being subtracted rather than multiplied, which it can look like if you are sloppy in your notation, if you just wrote a -1 over sine t here without a multiplication or without any parentheses, it would be very easy to misconstrue that as subtraction. And in that case, you would not be able to cancel. So remember, if you're uncertain about canceling something, try to rewrite it as a single piece and see if the thing you're trying to cancel is a factor, not just a piece, but a factor of the top and the bottom. So for example, here, if I had like x over u squared minus x, I could not cancel the x's. Because x is not a factor of the bottom, right? I cannot factor this x out. It's being subtracted, it's not being multiplied. So I'm appreciative of that question, and I think it's something that a lot of us need to make sure we really understand. Okay, having said all of that, what do I do now? Trevor made a comment in chat that the negative out front can flip the bounds. That's true. That's true. I could flip the bounds over. I could say this is positive integral root 3 over 2 to 1. I'm not going to do that though, because the square root of 3 over 2 is, oh wait, is that smaller than 1? I don't think for a minute. It is smaller than 1. Yeah, so there's a sense in which that would be the nicer thing to do, to get the lower bound smaller than the upper bound. So we could write this as integral root 3 over 2 to 1 with the negative gone. The negative can be absorbed into the integral, and the effect it has is flipping the bounds over. The other kind of rewriting thing I would do here is rewriting the inside as u to the negative 2 du, because that'll help me see my antiderivative. All right, what do I do now? This step optional, by the way. You don't need to do this, but it does have some aesthetic appeal. Looks nice.
Antiderive.
Good, and what is my antiderivative?
-1 over u.
Very good. And it's the presence of that other negative that made me hesitate here. The fact that we're going to get another negative when we take our antiderivative. So power rule works again here, right? We add 1 to the power and we divide by that new power. So this would give me u to the -1 divided by -1, which is -1 over u, but just being very, very careful here. My next move would be to do exactly as Trevor suggested and rewrite this as -1 over u. Evaluated from the 3 over 2 to 1. And now I need to plug in those bounds, subtract. And there's going to be some negatives piling up. There's going to be some fractions to deal with. So we just take it very carefully. This is going to be -1 over 1 minus -1 over root 3 over 2. And judicious use of parentheses is wise. The first piece is just -1. Minus minus here makes plus. And then the reciprocal 1 over the square root of 3 over 2 is 2 over the square root of 3. So that's your answer. Questions on this guy?
How did you get the, oh, do you hear me?
Yeah.
Oh, sorry. How did you get the 2 over square root 3 again with the reciprocal?
Yeah, so 1 over root 3 over 2. I think of this as the numerator is 1 over 1, and I'm dividing it by root 3 over 2. So that's 1 over 1 times 2 over root 3, which is 2 over root 3.
Oh, we're just simplifying. I thought we did some math. And I was like, I don't understand the math. We're just got it. Thank you.
Yeah, no, nothing fancy. I want to make sure I understand the question, Holly. Oh, because at this stage right here, yeah, you're right. Root 3/2 should have been my upper bound. Or not should have been, let me be clear. There's not a mistake here. Root 3/2 was previously my upper bound. But when I went from this step to this step, the negative out in front of the integral, I sucked that into the integral and flipped the bounds over. So the rule I'm using there is that the negative of the integral from a to b of f of x dx is the integral from b to a of f of x dx. So it's one way to help kind of clean up things. And it's optional, it's not necessary. If you left that negative out front and then did the evaluation in the other order, you would still come to the same answer. This reminds me though.
Yeah, you come to the same answer either way.
Yep, and in fact,
Okay.
remember there's another approach to this integral overall. This is actually, I wouldn't say this is the wrong way to do this integral, but this is certainly the long way to do this integral. What's the fast way to do this integral? What is sine t over cos squared t?
Tangent t.
Tangent t times,
Secant.
yeah. The fast way to do this integral, just for those who are wanting to hone and deepen those skills, is to rewrite this as integral 0 to pi over 6, 1 over cos t times sine t over cos t dt, which is integral 0 to pi over 6 secant t times tangent t dt, whose antiderivative is just secant t. Could be done much, much faster. This will get you there in like 4 steps. But we wanted a U-sub problem. We're doing it as a U-sub problem. So. All right. One other thing I wanted to kind of remind you guys of, and before we go, are some nifty tricks, useful properties of the definite integral that can be big time savers and also make for good true-false questions. There are a bunch of properties, and we've studied them all thoroughly, but there's just a few that I want to remind you of here. If f is an even function, continuous on the interval negative a to a, you can even relax continuity to just integrable. Then the integral from negative a to a of f of x dx can be done as the double of the integral from 0 to a of f of x dx. This is a symmetry thing. Because if your function is even, then the area from negative a to a really is just twice the area from 0 to a by symmetry. Even more useful, if f is an odd function, continuous
on the interval negative a to a, then the integral from negative a to a of f of x dx is just 0. No computation needed. Odd functions have their own symmetry, right? So something like this. Integrate from negative a to positive a, you'll have exactly the same amount of area negative on one side as you have positive on the other, and they will cancel perfectly. These are two super useful things. We refer to them as symmetry properties of the definite integral. And the second one especially, I could give you a problem where you don't know how to evaluate the integral. You can't find an antiderivative, you can't do the Riemann sum. But if you recognize that the function is odd and that you're integrating over an interval symmetric about 0, then you automatically know that the integral is going to come out to 0. This is a very nice thing. Trying to think if there's anything else like this while we're here. Okay. Yeah, that's what I want to say. All right, we've got just a few minutes left. Is there anything else, last minute stuff that you guys would like to look at before we call it a day and you are on your own to prep for the test?
Maybe I'll ask about what you just said. I feel like you're hinting at something, which I appreciate, but I don't think it's going to be as easy as like an x squared or an x cubed. So can you maybe give us like a harder example or something that's not as direct?
Yeah. So I could ask you for the integral from negative pi over 2 to pi over 2 of sine cubed theta plus these are all discontinuous at negative pi over 2 and pi over 2. Yeah, it's not sine cubed theta plus, a cube root of theta. Why not? This is not an integral you guys know how to do. Sine cubed it's not impossible. It's very possible, but it's a little bit tricky. Cube root of theta, you do know how to handle that, but together, because you don't really know how to handle sine cubed, this would be quite hard. I could conclude right away that this is 0 because the function f of theta equals sine cubed theta plus cube root theta is odd. How do I know that's an odd function? Well, I know sine is an odd function. And when you cube an odd function, you retain its oddness. The cube root is also an odd function, and the sum of two odd functions is odd. So if I asked you to evaluate this integral, you could just tell me it's 0 because you know this function to be odd. You need to be comfortable with function parity, right? You need to be able to recognize whether a function is even or odd. And since you don't have a graphing calculator, that means you need to be comfortable with function parity from an algebraic standpoint. You need to know how to recognize even and odd functions from their algebra, from their definitions. But yeah, that's it. There is an example in the textbook. I just don't remember exactly where it is. Something with a crazy like tangent and polynomial function. It's back here. Actually, it might have been. Oh, maybe it wasn't here. Let's see. Well, there it is back in the definite integral section. Yeah, probably.
If sine was squared, would it still be odd?
No, sine squared is actually an even function. So rather than me hunting through the textbook for this, maybe I can help you with some rules for even and odd functions, right? Let's just do rules for odd functions. So we're short on time. If f and g are odd, then so are f plus and minus g. The composition f of g, f cubed, or f to the fifth, or f to any odd power. That's it. Yeah. If you multiply two odd functions, the result isn't odd. But if you compose, meaning you plug one odd function into another, that's going to be odd. If you sum or add or subtract two odd functions, the result will be odd. And if you raise an odd function to an odd power, that's really actually a special case of this guy. So it might be worth your time, if you haven't done this in the past, to get comfy with the rules for even and odd functions. It's something we do in pre-calc, I think, but it's often not given the time it deserves. Similar rules for even functions. If f and g are even, then so are f plus or minus g, f composed with g. In this case, f times g, even times even is even. That works fine. And then any even power of an even function. Some other fun stuff, if you take an even function and an odd function and you multiply them, that's going to be odd. If you take two odd functions and multiply them, that's going to be even. What else like this is fun? If you divide two odd functions, that will be even. If you divide an odd function by an even function or vice versa, that will be odd. Try to come up with some rules. The names even and odd come from somewhere. They hold similar properties to even and odd numbers, but you have to think about which operation corresponds to which operation. So it's a fun thing. But if you're ever in doubt, remember odd functions. You can always check. An odd function is one that satisfies f of negative x is the negative of f of x, and an even function is one that satisfies f of negative x is the same as f of x. And it's worth remembering which trig functions are even and odd. Sine and tangent and cotangent, sine and tangent are odd. Yeah, cotangent is also odd. Cosine, secant are even. I think cosecant is going to be odd. So yeah, knowing those facts and being comfortable with even and odd functions is useful. This is not going to be a big part of the test, but it could show up in one place or another. All right, that's what we've got time for today, guys. So I got to go ahead and end class. Got another one coming up. If you do want to talk more, you can come see me in my office hour, regular office hour today from 1 to 2 p.m. I will try to throw in an extra office hour over the weekend, although I can't make any promises. It's going to be a pretty busy weekend. But because we did miss one earlier in the week due to my jury duty, I would like to get one extra one in there if I can. So I'll post an announcement about that if we're able to do it. But if you need to chat, please come by this office hour today. And that is it. I'll see you guys for the test on Monday.